So our geometry and meshing is done. Now we will do the case setup and solution. So in order to do that, let's start the Fluent. So open the Fluent. Here the Fluent interface. So check your case. You will see the minimum volume, that is positive, so you don't have any problem with your geometry. You can check the quality. Right now the minimum orthogonal quality is 0.2, which is not very good, so you need to increase your number of mesh and number of nodes, but we will do with this mesh right now for demonstration. So we will do a pressure based solver and steady state problem, and the velocity formulation is absolute. So go to model. According to our problem setup, our Reynolds number is 500, which is laminar flow. So in the viscous option we will use the laminar flow, and we will turn on the energy equation. In the material section, the default material is air. We need to change that, so we will do exactly the same thing that we did in 2D. So change it, copy, and change and create. Now air. In the cell zone condition, we have the fluid air. We need to change it from air to water liquid. Now the boundary condition, which is very important. In the inlet section, we already calculated the inlet velocity based on Reynolds number 500, that is 0.0197 meter per second. So we will put that inlet velocity 0.0197, and for thermal it should be 353 Kelvin. For outlet, we have outflow, so change it from pressure outlet to outflow, and the wall has a fixed temperature, that is 25 degrees C or 298 Kelvin. Okay, now we don't have any dynamic mesh. Our reference value, you can check the reference value. These are the reference values. Our solution method, we will use simple solution method with least square cell based discretization and standard discretization for pressure, and second order upwind for momentum and energy. Solution control, we will keep this as it is. Monitor section, we will see the residue, and we will initialize our solution. So it will initialize the solution, and then we will run our calculation 100 times. So it will start calculating, and as you can see, both the continuity, the momentum, and the energy residue are reducing. So it's a good sign that your solution is converging. So you run this calculation according to your convergence criteria, and after it finished the calculation, we will see the results, and we will try to compare the results with 2D flow. So we did 100 iteration, but the solution is still reducing the residue. So we will do another 100 iteration, and we will try to see whether it converges or not. As you can see here, we have a fluctuating behavior for both continuity and the velocity. So there is some different kind of error propagation which influences a lot during the solution. You can easily see the behavior of your solution, and you can change the relaxation factors and other things if you want. So right now you can see here your propagation is much higher. That's why we have a fluctuating behavior here in the momentum and continuity. But in the energy equation, it doesn't change too much. So for example, if you change any temperature of your boundary condition, only your energy equation will change. If you want to see, I can show you. In the wall section, change this temperature from 298 to 310. That's it. Okay, and run it 100 times. Then you will see a sudden change in your energy equation. So that means in the energy equation the temperature changes a little bit and it changes the solution, and again it tries to converge after some iteration. So this is the interesting things in Fluent. There is lots of things you need to understand. So the solution is done. So right now we will see the velocity and temperature contour, and we will try to see the plots for 3D. So go to graphics and animation, contour, and we will create the plane. So go to new surface and isosurface, mesh, and we will see how far it goes. So before do that, let's change the unit from meter to inch here, and then go to surface, isosurface, x coordinate, compute. So it goes from minus 0.5 inch to plus 0.5 inch. For y coordinate compute, it also goes the same distance. For z coordinate, it goes from 0 to 30 inch. So we can change either x and y. So if the iso value is 0, that means it will create a plane at the middle. So iso value right now is 0. Let's name it plane 1, create. And if you want to see the plane, go to mesh, setup, inlet, outlet, wall, outline, display. Now you can see only the tube here. If you select the plane and display, now you can see the plane inside the tube. So we will see the velocity, temperature and pressure contour in that plane. So go to contour and select plane 1, select the velocity, velocity magnitude, display. Now you will see the velocity distribution here. So this is the inlet, change it to fill and make it okay. So this is your velocity distribution, which is kind of similar to the 2D solution. If you want to see the temperature distribution, go to temperature, static temperature, display. Now you can see the temperature distribution also, but we will see in plot section how this varies with 3D problem. So in order to do that, we need to draw the line. So we will develop the line. So select the line, and as this is a 3D drawing, that's why we have 3 coordinate system x, y, z. So we know what value we have to change. We need to change the z value first of all, and obviously the x and y value accordingly. So let's say in the mesh section, so this is your coordinate. Here this is your coordinate system. This is 0, 0, 0. At this point you have a translation in the z direction, but your x is 0, your y is 0, and at this point you have translation in z direction, your x is still 0, but your y is 1. So here you can see, the coordinates for the first line. We have in the x equals to 0 plane, so each and every point in x equals to 0 plane, our x coordinate will be 0, 0, and our y varies from -1/2 inch to +1/2 inch, and only thing will vary, that is the z. First of all, it's 1 inch, 1 inch. So this is line 1, 1, create, and if you want to see line 1, 1 display, you will see here. But this is our outlet, so we need to draw the lines at our inlet. So our inlet is here, 30 inch apart. So we will play with the z, so it will be 29, 29, create. It will be, let's name it line 21, create, line 21, display. This is our first line. Our next line will be 28, 28, that would be our line 22, 22, create, display. Our third line would be 27, 27, that would be 23, create, display. And fourth line would be 26, 24, create, 24, and the final fifth line will be 25, create, display. So this is the 5 line we have created. We already saw the velocity contour. We will see the plot along this line. So go to plot and XY plot, select the velocity magnitude, line 21, plot. So it's a single line. We will change it from here, and we will change it with the direction vector. So here you can see the velocity distribution. As our number of mesh elements is much lower, that's why we have a very discrete point. We don't have any regular distribution. If you select line 22, we will see the change, velocity magnitude, line 23 here. So the velocity is developing. Line 24 is right now parabolic, and 25 is totally parabolic distribution. So here you can easily see the velocity boundary layer, and the velocity distribution. In 1 inch from the inlet, the velocity distribution is the red line here. In the 2 inch from the inlet, it's developing. 3 inch still developing but taking the parabolic shape. 4 inch and 5 inch perfectly parabolic. So you can see the momentum boundary layer and the entry length. So this is the process. You can also see the velocity distribution and the temperature distribution for 3D problem, but it's always better to do the 2D problem first to predict the flow field. The advantage of doing 2D simulation is you can save a lot of time because it will take less mesh, and when you have small number of mesh elements, then your computational time will be much lower than the 3D mesh. So in the next tutorial we will see some mixing problem, and we will also see some heat exchanger problem. Thank you.